Okay, let's start off with some examples where we actually conduct a hypothesis test. So, for starters, let's look at this one. We have a random sample of 40 fifth graders in a particular region, and they're given a national standardized test. On this test, a score of 100 represents mastery of the subject. We can assume that the population standard deviation for all fifth grader scores is 18. And for this particular sample, the mean score is 95. We want to know if this group of fifth graders does seem to differ from the mastery score on their knowledge of the subject area. And we're given a significance level of 0.05. Okay, so let's start off. I like to write down the sample information first. Everything that we get from the sample, and this is just a matter of pulling it out of the paragraph. So what do we find first? Our N, our sample size is 40. Our sample mean, which is represented by X bar, that's 95. What else do we know? We do know the population standard deviation, which is 18, or we're allowed to assume it. So that would give us a sigma of 18. Notice I'm using sigma because it's a population standard deviation. I would be using S if this information was just for the sample. Okay, so now our next thing is to write down our hypotheses. And I tend to organize my work into 6 little boxes, either across or down, whatever works for your space. So next thing I want to do is write down my hypotheses. Okay, so for this we need our H0 and our H1 or our HA, whichever you want to call it, our alternative hypothesis. Okay, and so for this we need to decide what our benchmark is. So what are we trying to find out? We're trying to find out if the population of fifth graders represented by this sample, so that would be the population in this particular region of the country, we want to figure out if that population seems to be different from 100 or not. So what that means is our population different from 100? So 100 is my benchmark, so for my H0, I have mu, that's my population mean, is equal to 100. That's the hypothesis that we're going to test. So then our alternative hypothesis is also going to have mu in it. And so now we need to decide if we have a one-tailed test or a two-tailed test. So what we need to do is we need to read the problem and see if it is steering us in a direction. So if I look here, this group of students differed from the mastery score. So this is where I'm looking when I decide one-tailed or two-tailed. So I'm trying to decide if this differs from the mastery score. So if it said is higher from the mastery score or is lower than the mastery score, then that would tell me I had a one-tailed test. But since it doesn't seem to be steering me in one direction or another, then that means that I have a two-tailed test. So my alternative hypothesis will simply be mu is not equal to 100. And here with the hypotheses, I usually write down my alpha as well. And so my alpha is going to be what? 0.05. That's my significance level. Notice that this means that my confidence level is 95%. So sometimes they'll give you the significance level, which is normally written as a decimal. Sometimes they'll give you the confidence level, which is normally written as a percentage. If you're given the confidence level, you need to make it a decimal and subtract from 1 to get your alpha. But in this case, we have our alpha for free because they gave us the significance level. Okay, so now we want to do our sketch. Okay, so for this, I'm going to draw a curve. Like this. and I'm going to mark it. So what I need to do is I need to draw my shaded regions. And so since it's a two-tailed test, my shaded regions are going to be on both ends. And each of them is going to have alpha over 2 in it. So here we've got alpha over 2, so that is going to be 0.05 over 2, which is going to be 0.025 over in this shaded region. And so then the same thing over here. My alpha over 2 is going to be 0.025. Okay, and I'm going to go ahead and mark my critical values on the graph. Okay, so that's going to be where the color changes. So right here and right here. And we're going to, should these be z values or t values? Here's something else we need to think about is, are my assumptions met? So my rule of thumb on my assumptions is that I need to know for sure that the scores are normally distributed, or be able to assume that, or alternatively, I need to know that my sample size is at least 30. And in this case, the answer is yes. Okay, so that means we are okay on our assumptions. Okay, so on my picture, that means what that means is I can do this test, and it turns out the reason I'm using z's and not t's is because we actually know the population standard deviation. As we've discussed before, often that's not realistic, so it turns out a lot of times we need to use the t-distribution, and we'll move on to that later. But for now, we're going with z's, 0.025, and so then over here, this is going to be negative z 0.025. Okay, so that is my picture. So now what I want to do is I need to find the critical value to go onto that picture. And I'll probably have to do a little bit of scrolling back and forth to the problem here. I apologize for that, but that's the only way to make everything fit. These are big problems. Okay, so to find our critical value, what we need to do is we need to use our normal distribution table. Okay, so to find my critical value, what I want to do is I need to think about the fact that the area to the left, so if I just look at this z 0.025 here, okay, so I've got the area over here, so this area is 0.025. And so that means the area of the rest of it, all this stuff, is going to be what? So this area is equal to 1 minus 0.025, which is 0.975. Okay, so then what I do is I look up area equals 0.975 in my normal table. Okay, so let's go to our normal table. Okay, so let me go down to the positive z-score region because we're looking for 0.975. Okay, so where is that? We want to get as close as we can. You may not hit it perfectly. Ooh, it looks like we do hit it perfectly. Looky there. Okay, that's not always going to happen. So, as we've talked about before, if it ends up in between, if it seems to be about halfway in between, just split the difference. If it's much closer to one than the other, then choose the closest. So what is that going to give me? 1.9 for over here. And then this. So that looks to me like 1.96, right? That's a very important number in statistics because it comes up all the time because it's associated with the two-tailed 95% confidence interval. So then that gives me z.025 is equal to 1.96. And remember the trick that we've talked about before is if you want to go with the area of negative 0.025 using the symmetry of the normal curve, then you could have also looked it up in the negative portion of the z-table as well. Okay, so now I'm going to go add those to my picture. So this is going to give me positive 1.96 over here and then negative 1.96 over on this one. Okay, so now what we need to do is we need to calculate our test statistic. Okay, so what you want to remember on your test statistic is you are always, what you're trying to do with your test statistic, you're going to subtract what you're comparing and you're going to divide by the standard error. So let's figure it out, our standard error. So this is the standard error of the sampling distribution of the sample means. So this is the set of all possible sample means. Okay, so this is going to be the standard deviation of the set of all possible sample means. It's going to be sigma divided by the square root of n. And so my sigma, remember, is what? 18, and my n is 40, right? So we have 18 divided by the square root of 40. And it turns out that that is approximately 2.84. And I normally do this step separately instead of trying to do it inside that fraction. And that ends up making my life easier when we get to some of the more complicated tests and the standard error is not such an easy calculation. I'm just always in the habit of doing standard error, then my test statistic. I always do them in that order. Okay, and so then to do the test statistic, what we do every single time in every different type of hypothesis test is we subtract whatever we're comparing and we divide by the standard error. That's the way it always works every single time. So in our case, our test statistic we can call z. And so this is going to be my x bar minus my benchmark divided by my standard error. Okay, and so when I put in numbers for that, what am I going to get? My x bar is what? 95. So that's the sample mean of my sample. And then what's my benchmark? 100 from my null and alternative hypotheses, right? So we do 95 minus 100. We divide by that 2.84. And usually I store that 2.84. I think this is actually 2.846. Usually I don't worry too much about which one I write down, but I normally store that entire value, all the decimal places in my calculator. And then, like for example, store it in variable A, and then I do 95 minus 100, hit enter, divide by variable A. Make sure that you either put parentheses around your numerator or that you hit enter after your numerator, or else you're going to get an order of operations mistake and you're going to get the wrong answer. Okay, so it turns out that this is about equal to negative 1.75. Okay, so let's go back to our picture and let's put that on our picture. So where is negative 1.75? It's not in the rejection region, is it? It's around here somewhere, right? Okay, so I just usually mark it, and it's easy to look at the picture and see whether it's in the rejection region because we already have our critical values marked on there. And so there we have that. And then what we want to do is write our conclusion. Okay, and so my z equals negative 1.75. This is not in our rejection region. And so what that means is we do not reject H0. Okay, and so that is part of our conclusion. We definitely want to have that. But we also want to write our conclusion out in words in terms of the original problem situation. And so for this, we need to realize that it's going to be sample specific. So this sample does not provide evidence that this population of fifth graders differs from that mastery score of 100. And there's not a magic wording that it has to be just like this particular wording. But what I want to see here is that you say something that you understand what this do not reject H0 is telling you. It's telling us that the sample doesn't provide evidence that this group of students is difference from this benchmark number on average. Okay? It does not prove that they're the same or anything like that. All it says is that we don't have evidence of an interesting difference or an effect or what we call a statistically significant difference from 100 here. Okay, so this is the general way that we do a hypothesis test.